Hello everyone, welcome to my video where I will be presenting my original research on the tunable optical properties of halide-based inorganic materials. My name is Alice BlackBear. I'm an undergraduate, a senior in the Department of Chemistry at Colorado State University Pueblo. And let's get started. So to begin, I would like to take a moment to briefly outline what we will be discussing today. Firstly, I will give you all a short introduction to materials chemistry. Then second, I will show you the work we've done with some photoluminescent systems. Then we will discuss the synthesis and properties of some thermochromic pigments. Lastly, we will discuss the future directions of our lab group and some acknowledgements. To understand materials chemistry, we first must understand what material science is. Material science is the interdisciplinary approach to understand a given material's structure, composition, and novelty. Engineering, physics, and chemistry all come together to form an emerging and exciting field of study that will solve many, many problems in the world. As such, even within the materials chemistry subfield, you can find many specializations that all seek to answer some of these very important questions that we have about a given material. In our lab at CSU Pueblo, we primarily focus on solid-state inorganic materials chemistry. So, let's discuss some of the relevant materials we made in our lab. First, we have a hydrated rubidium-indium chloride complex with a given empirical formula that exhibits a very vibrant orange fluorescence at 280 nanometer excitation. These photoluminescent materials have applications in photovoltaics, as LED components, and even as luminescent thermometers. Our sample is synthesized using a method from Pat Woodward's group at The Ohio State University, which simply involves a very easy to do solvent precipitation of the rubidium chloride and indium chloride salts, as well as a 0 to about 5% antimony 3+ dopant. That resultant precipitate is white under normal light, but as previously stated, and as you can see in the picture, it emits that bright orange color when excited with UV light. We know that for this complex and the non-hydrated complex of the same variety with the rubidium and indium, that the emission occurs because of the antimony 3+ activator and the resultant asymmetry in the crystal lattice. The space group of this complex was previously reported on by Pat Woodward, and with our preliminary structural refinements, we also confirmed that it was the correct space group. The next material we synthesized was the non-hydrated rubidium-indium chloride complex. Some of these non-hydrated structures can have the water removed from their crystal lattice reversibly, such as the cesium derivative, with heat and the correct organic solvent. Dr. Woodward's group at the OSU reported using a sonicator and acetonitrile to remove the water, whereas at our university, CSU Pueblo, we actually ran into some experimental difficulties with our sonicator instrument. As such, we actually needed to find another means then to verify that heat and acetonitrile were effective at removing water from the lattice. What ended up working for us was using our microwave instrument and then the following parameters. As you can see, 300 watts, 25-minute hold time, 100 psi, and 79 degrees Celsius. These power, pressure, and temperature thresholds were very important to the success of the synthesis with the microwave instrument. We did spend a great deal of time and effort testing the correct combination of these parameters. And again, with respect to that space group, it was previously reported by Dr. Pat Woodward, and we confirmed that with our preliminary data And we also confirmed that the antimony 3+ activator was vital for the green emission that you can see in this picture. Now that I've made some claims regarding our work, let us go ahead and look at the actual data. Here we have the preliminary polyfit for the hydrated rubidium indium chloride complex. In pink, you can see the calculated fit compared with our experimental powder X-ray diffraction data in blue. The fits you will see today were all done using the free GSAS2 software. For this particular fit, the RW value was around 7.2, which indicates a decent preliminary polyfit. And the unit cell parameters in the table were provided also by GSAS2, and they closely fit the previously reported data. And here we have the powder X-ray diffraction data and the fit for the non-hydrated rubidium indium chloride complex. For this fit, the RW was slightly higher, and this can be seen by the deviation in our red calculated data versus our black experimental data. However, we believe this had something to do with unideal experimental conditions with our microwave synthesis, meaning that there may have been some hydrated phase contamination somewhere in the lattice, but that's yet to be determined with some further experimentation. And you can see here that the unit cell parameters closely match the previously reported data. Now, you may be wondering where we wanted to take our research, given that I've only shown you how we verify previously reported data. The direction we wanted to take this research was towards understanding the optical properties of the non-hydrated rubidium indium chloride phase, given that that structure was only previously reported. Here we have a temperature-dependent emission plot along with a CIE plot and a modified Arrhenius plot. From the emission data, we see clearly that with increasing temperature, there's thermal quenching, which could be the result of non-radiative recombinations. The quenching was one of the two expected outcomes for this type of material, but since there is not a direct trend, it was not initially hypothesized to exhibit this property. The emission data gave us the information we needed for the modified Arrhenius plot, which gives us an estimation of the activation energy, which you can see there. Now, ideally, it would have been better to have low temperature emission data with a low temperature modified Arrhenius plot. However, due to experimental issues, we were not able to provide that data today, but that is one of our ongoing projects. Now, I would like to shift gears just a little bit to discuss another project we're doing in Dr. Wallace's group. That project is related to inorganic pigments. We initially set out to synthesize another non-hydrated rubidium-based halide complex with a similar unit cell in order to understand its structural properties and maybe its relationship to the rubidium indium chloride analog. This led us to the thermochromic inorganic pigment with a general structure similar to that of the indium-based structure. Additionally, inorganic pigments have been receiving a lot of attention lately with the creation of moss blue at Oregon State University. With that in mind, our group scoured the literature for an ideal structure, and we came across a paper that had the rubidium and NH4+ based iron chloride complex, pictured here. The previous work gave us a chance to test the synthetic route as well as the material's thermochromic properties. My work focuses on the rubidium-based structure, and that is the one we'll be discussing today. It has a similar space group to the indium analog, but the properties of the material are very different. as evidenced by the fact that it is orange and thermochromic under white light, whereas the indium analog is strictly a white powder. The synthesis of such a material was the exact same, however, which was interesting that changing one atom gave us a totally different material with totally different properties. Having correctly synthesized the hydrated version of the rubidium iron chloride-based structure, and also the non-hydrated version of the indium analog, the question had to be asked: does the same approach to removing water from crystal lattices for the indium analogs work for the iron-based inorganic pigments? I set out to answer this question with my research, and that is exactly what I am doing now in the lab. So I applied the same parameters with the microwave instrument as before: 300 watts, 25-minute hold time, 100 psi, and 79 degrees Celsius. The material I isolated from the solvent afterwards was the yellow powder shown here. The color of the powder did not change, however, with increasing temperature, and I found that rather interesting since the precursor was very responsive to changes in temperature. Now, as of today, and also because this is the work I'm currently doing, I'm waiting on temperature-dependent structural data to confirm or deny if I made that material. But by the time of the conference, I will have definitive data to share, so please stay tuned and maybe I will see you there. For now, we can go ahead and look at the structural refinement done for the hydrated rubidium iron chloride structure. As you can see, this fit is relatively close to the experimental data, supporting that our estimate of the space group was correct. The provided unit cell parameters were also close to previously reported values. And here, we have some interesting data to share. Since the material does not emit with 280 nanometer excitation, and since it shows thermochromic behavior, we thought it would be appropriate to use temperature-dependent diffuse reflectance spectroscopy in order to estimate the optical band gap of our given materials. As you can see, with increasing temperature for both of these materials, the rubidium and NH4-based iron chloride compounds, the optical band gap actually decreases. Now, admittedly, I am relatively new to materials chemistry, so I could not exactly say if this was expected or not. But I do plan to perform the same experiment again with our potentially non-hydrated rubidium iron chloride structure to see if the trend is the same or different. And I will also be doing some research into the expected trends with optical band gap for a given material to learn if this was the expected trend or not. Now, lastly, as I stated before, we did not have low temperature data to confirm or deny any of these trends, but that is going in development in our lab as we speak today. So I wanted to take a moment and go over some ideas on where we would like to take our research. Primarily, we want to find and synthesize additional 1+ ion iron-based inorganic pigments in order to see if we can find that elusive red pigment that everyone is searching for, and also to see if they have similar optical properties to the ones that we've already made. We're also going to confirm the space group of my possibly non-hydrated rubidium iron chloride compound, and I hope to learn a bit more about the electronic transitions of these materials with Moss-Bauer spectroscopy, which is only done in a few places at the moment, but for sure we know that it's being done at the Oak Ridge National Lab. And since, again, that red, or the vibrant red rather, is the elusive inorganic pigment, we're going to study irreversible thermochromism and metal halide complexes to see if that is one avenue to a vibrant red compound. And lastly, as stated previously, we're going to work with a low temperature setup for optical and structural data in order to identify any relevant trends in the given material. I want to take just a few moments before I go to do my acknowledgements. I want to thank first Dr. Dimitri at University of Alberta for the structural characterization that he did for us, as well as to the MAPS and McNair programs at CSU Pueblo for sponsoring my research and my travel to this wonderful conference. And lastly, I want to acknowledge the fellow members of my research group, as well as Dr. Max Wallace, for the encouragement and assistance I needed to make this presentation possible. If you have any questions, please let me know in the comments, and we will see you at the conference. Thank you.